Okay, let's jump right into this explainer and tackle our main topic, cracking the matrix a to the power of 20. It's a math problem that, honestly, looks completely terrifying at first glance. If you've ever stared down a complex equation and felt that sudden, sinking wave of panic, you are absolutely not alone. Today, we're looking at what seems like an impossible calculation, but we're going to do it differently. We're putting on our detective hats. We aren't just going to crunch numbers. We're hunting for the hidden architecture underneath them. Because, in advanced math, things are rarely as grueling as they first appear. There's almost always a secret backdoor, a really elegant shortcut designed to reward whoever is paying close attention. Take a look at this. Here we have an authentic, incredibly high-stakes question from the upcoming 2026 CSIR-NET/JRF mathematics exam. Now, this is a major competitive exam used to determine eligibility for lectureships and research fellowships, so the pressure is absolutely immense. The question asks us to find the value of a matrix, let's call it matrix A, raised to the power of 20. The initial matrix A is a standard 2x2 grid. The top row is 3, -2, and the bottom row is 2, -1. And the question gives us 4 multiple choice options for what this matrix is going to look like after it's multiplied by itself 20 times. Now, what's really wild here is the sheer dread this question induces. I mean, are we genuinely expected to sit there in a quiet, high-stress exam hall and crunch through 20 tedious matrix multiplications? If you remember matrix multiplication from algebra, you know it's not exactly a quick process. You're multiplying rows by columns, adding the products together, mapping them out. Doing that once takes a minute or two. Doing it 19 times to reach the 20th power, that would literally take pages of scratch paper. It's incredibly time-consuming, and worse, the chance of making a tiny arithmetic error, like, dropping a negative sign or misadding a single digit, is astronomically high. Actually, if you make a mistake on step 3, steps 4 through 20 are completely busted. So there is no way the test makers actually expect us to do this the hard way.
So, step 1, gathering mathematical clues. Instead of panicking and defaulting to brute force, let's treat this matrix like a puzzle box and just unlock the first 2 layers.
And this perfectly illustrates our strategy. We just need a little bit of initial data. So we calculate a squared, which is just multiplying matrix A by itself one time. When we do that, we get a new matrix. The top row becomes 5, -4, and the bottom row becomes 4, -3. Now, we could calculate a to the power 3 next, but an even better shortcut is to just multiply a squared by a squared. That instantly gets us to a to the power 4. When we do that second calculation, our new matrix has a top row of 9, -8, and a bottom row of 8, -7. And let's just stop right there. 2 calculations. That is literally all the manual labor we are going to do today. Moving on to our next phase, spotting the hidden pattern. We have our initial clues, so let's see what they're trying to tell us.
We've got 3 points of data now. Our starting matrix A, which is to the power of 1, our matrix A squared, and our matrix A to the power of 4. Rather than looking at the whole grid of numbers and getting totally overwhelmed, let's isolate just one single position. The crucial point is right here on this table. Let's focus our attention exclusively on the top left corner, and look at how the exponent, which we'll call n, maps to that number. When our exponent is 1, the top left number is 3. When our exponent is 2, the top left number is 5. And when our exponent jumps to 4, the top left number jumps to 9. Do you see it? We're looking for the relationship between n and that top left value. It's a linear progression revealing a beautifully simple hidden formula. 2 times n plus 1. Let's test it just to be absolutely sure. If n is 1, 2 times 1 is 2, plus 1 is 3. Matches. If n is 2, 2 times 2 is 4, plus 1 is 5. Perfect. If n is 4, 2 times 4 is 8, plus 1 is 9. It's a 100% perfect match. We've basically found the matrix's DNA.
Once we spot that this top left position is always 2n plus 1, the rest of the matrix positions instantly fall right into place, totally saving us from doing pages of manual algebra. Look at how the other numbers relate to the exponent n. The top right number is always -2 times n, the bottom left number is always exactly 2 times n, and the bottom right is always -2n plus 1. The entire matrix is literally just a reflection of whatever exponent we happen to be looking for. It's like a perfectly synchronized machine. Now for the really fun part, finding the final answer. With the secret code cracked, we can skip straight to the end of the puzzle. We don't need to know what a to the 5th or the 10th or the 19th power is anymore. We have the master key. If we plug our target exponent of 20 into our simple 2n+1 pattern for the top left corner, the math becomes something you can do in your head in about 2 seconds. 2 times 20 is 40. 40 plus 1 gives us our magic top left number, 41. Boom, that's it. That right there is the anchor for our entire final matrix. Looking back at our multiple choice options from the exam, we are hunting for the matrix that starts with a 41 in the top left. And look at that, option B perfectly aligns with our magic number. If we check the rest of our pattern rules against option B, they all hold up perfectly. The top right should be -2 times 20, which is -40. The bottom left should be +2 times 20, making it 40. And the bottom right completes the pattern as -39. We have our final matrix. 41, -40, 40, and -39. We arrived at the absolute correct answer without ever needing to calculate a to the 5th, let alone grinding all the way to the 19th and 20th powers.
So what is the big takeaway here? Let's step back and look at what this elegant solution teaches us about efficient problem solving. It is so easy to get tunnel vision when we're presented with a straightforward but tedious instruction like multiply this 20 times. We often just put our heads down and start working because the path is obvious, even if it's painful. But taking a pause to understand the structure of a problem is always a better investment of your time. This perfectly highlights why taking a deep breath and finding the underlying pattern is vastly superior to blindly grinding through brute force arithmetic, especially under intense exam pressure. Brute force would have cost a student 10 to 15 minutes and carried a massive risk of a single arithmetic error just derailing the entire question. Pattern recognition took 2 simple calculations, maybe 2 minutes of thoughtful observation, and yielded a precise, mathematically guaranteed result. It really is about working smarter, not harder. And that leaves us with a fascinating final thought for this explainer. Think about your own life for a second. How many other seemingly impossible tasks sitting right in front of you, whether in a math exam, in computer programming, or even just organizing your daily workflow, are actually just simple, elegant patterns waiting for you to spot them? The next time you're faced with a massive, repetitive task, don't just start grinding away. Stop. Calculate the first few steps. Look for the hidden rule. You might just find your very own master T.